Welcome to the deep dive. We're really going beyond the headlines today.
Okay.
We're looking into something fundamental, manufacturing, specifically high precision machining,
Mm,
and exploring how advanced software is genuinely shaking up this really old industry.
yeah, let's go at the transformation.
We're talking about getting, unprecedented efficiency, cutting costs, and maybe even bringing some production back home.
Which is a huge topic right now.
Absolutely. So for this deep dive, we've gathered quite a bit. A YouTube transcript, company profiles, product details, a Siemens white paper, and various news bits and blog
A
articles.
good mix of sources there.
Our mission really is to grasp how this blend of machining dynamics, the physics of it all, and AI is taking the guesswork out of these super complex jobs.
It's about moving beyond intuition, right?
Exactly. Transforming those traditional machine shops and tackling big issues like the skills gap and, well, the need to be more sustainable.
And for any manufacturer, especially dealing with metal parts for, say, aerospace or energy,
Demanding sectors.
very demanding. The core challenge, it always comes down to this balancing act. You need speed, you need quality, and you absolutely have to control costs.
It's like a three-legged stool, isn't it?
It is. And traditionally, you often had to compromise on one. Faster might mean lower quality, or higher quality might mean way higher cost. Finding that sweet spot was tough.
Okay, so let's unpack that. What made it so hard for so long? What were those traditional hurdles?
Well, a big part of it was this endless cycle of trial and error, iteration after iteration.
Just keep trying things.
Yeah, machinists, even really experienced ones, would essentially make an educated guess at the best settings. Run a part, check it, tweak something, run it again.
Sounds slow and expensive.
Incredibly slow. Wasted time, wasted materials, wasted energy. Sometimes it could take weeks just to get one part optimized. Weeks of just guessing and checking.
And a major reason for all that guesswork was this thing called chatter vibrations, right? What exactly is that? Sounds bad.
Oh, it is bad. Chatter it's basically the machine tool system vibrating uncontrollably during cutting.
Like shaking.
Yeah, but in a very specific, destructive way. It happens when the cutting process excites the machine near its natural frequencies. Think of like hitting a tuning fork.
Okay.
And when that vibration gets unstable, you get chatter.
Hmm.
The consequences. Well, poor surface finish on your part, dimensional inaccuracies.
So the part isn't quite right.
Exactly. Plus, it chews through your cutting tools much faster, which means higher tooling costs. Can even damage the machine itself over time, leading to more maintenance. And it's loud.
And you often don't know what's happening until it's too late.
That's the kicker.
Yeah.
Often you only spot it afterwards. You see the marks on the workpiece, or your tools are just wearing out way too fast. You're reacting, not preventing.
Right. This isn't just theory, though. Let's ground this in a real example. There's a company, AML Advanced Manufacturing, Rotherham, Ltd.
I know them.
They do subtractive machining, mostly metals, for aerospace, energy think gas turbines, jet engines,
Critical components.
very critical. And they face this challenge. A big Tier 1 aerospace supplier was having delivery problems with their previous supplier for a jet engine part.
Okay.
So IML got the call, but it was a tight deadline, a 6-month contract to make 3,000 of these components.
Wow, that's pressure.
Yeah. And here's the interesting part. AML, they're good. They'd already optimized their process using all the standard engineering techniques.
Pushed it as far as they could traditionally.
Right. They got the cycle time down to 1 hour per part, but they said they were, and I quote, stuck at that point.
Yeah, that really shows the ceiling of the conventional approach, doesn't it? When you've done everything by the book and you still need more.
So you hit that wall. How do you break through? What kind of new thinking or technology is needed?
Well, in this case, the breakthrough came from a company called Productive Machines. And their origin is quite interesting. They actually spun out of the AMRC, the Advanced Manufacturing Research Center.
The one with Boeing.
That's the one.
Okay.
Boeing was actually their first investor. And this wasn't just some startup idea. It's based on over 20 years of deep R&D into machining dynamics.
Right, so serious science behind it.
Very serious.
And the person really driving this is Dr. Erdem Osterk, co-founder, managing director. Tell us about his background. Seems important here.
Oh, definitely. Dr. Oster, he has a PhD in mechatronics engineering, and his focus was specifically on modeling multi-axis machining.
Tailor-made for this problem.
Pretty much.
Yeah.
He's also senior technical fellow at the AMRC, leading their digital machining work, and he's involved with CIRP, that's the International Academy for Production Engineering.
So top-tier credentials.
Absolutely. It signals that this isn't just, clever coding. It's built on a really deep understanding of the physics involved. Rigorous stuff.
So what's the core tech? Productive Machines has this SenseNC suite. What is it?
Okay, so SenseNC. It's described as autonomous milling optimization software. Think of it like this. It takes all that deep knowledge of machining dynamics, the physics, adds AI into the mix,
Hmm.
and uses it to simulate just countless possibilities for how to machine a part. It's predicting and preventing problems like chatter before they even happen.
It's like digitizing that master machinist's intuition we talked about.
Exactly. But faster, more precise, and based on actual physics models of that specific machine. It takes the guesswork, the black art, out of it.
Okay, and within SenseNC, there are specific tools. Let's talk about SenseNC Finesse. What does that one do?
Finesse is laser focused on killing that chatter vibration. That's its primary job.
Getting rid of the shakes.
Yep. And once it ensures stability, it optimizes the spindle speeds and the feed rates, how fast the tool spins and how fast it moves through the material.
How does it know what to do?
It takes everything into account, the cutting parameters you want to use, the material you're cutting, the specifics of the machine tool itself, and analyzes the entire tool path point by point. It does need one thing first, though, a quick tap test.
A tap test, like hitting it with a hammer.
Sort of. It's a bit more scientific than that. Usually involves an instrumented hammer and sensors. But yeah, you basically tap the machine structure to measure its unique dynamic properties, its natural frequencies.
It's fingerprint almost.
Exactly. Once it has that fingerprint,
Mm-hmm.
Finesse can design tool paths that are guaranteed to be chatter-free, smooth sailing.
Okay, makes sense. Then there's SenseNC Feeds. What's its specialty?
Feeds focuses, as the name suggests, purely on optimizing the feed rates. But it does this based on calculated cutting forces, the stresses on the tool itself, and crucially, the machine's own power and torque limits.
So it knows how hard it can push the machine without breaking something.
Precisely. The goal is maximum productivity, pushing the feed rates as high as safely possible without breaking tools, which is obviously expensive and causes delays. It eliminates that whole trial and error process for feed rates.
Wow. So this software takes something that, as you said, could take a machinist years of experience and guesswork to figure out.
Literal years, sometimes.
And does it in minutes?
In minutes.
Oh,
That's the
yeah.
power. It simulates and calculates the optimal parameters incredibly quickly.
That sounds like it could really help with the skill shortage everyone talks about in manufacturing.
Oh, massively. Finding those master machinists with 30 years of intuitive knowledge is getting harder and harder.
Right.
This tech democratizes that expertise. It allows less experienced operators to achieve really high levels of optimization safely and efficiently. It puts that power in their hands.
And it's easy to use, integrated with standard software.
Yeah, they've made a point of that. It integrates directly into Siemens NX CAM, which is, a very widely used platform in the industry. So it fits into existing workflows pretty seamlessly.
Okay, theory and tech are great, but let's talk results. Let's go back to AML, stuck at 1 hour per part, needing to make 3,000 of them fast. What happened when they used this?
This is where it gets really compelling. Productive Machines came in, applied their SenseNC software, and they reduced AML cycle time by over 20%.
20%, just like that.
Well, not just like that through applying the software optimizations, but yes, a significant jump from where they were stuck.
That must have made a huge difference to their bottom line on that contract.
Absolutely. It meant they could pass on significant cost savings to their Tier 1 customer. And that competitive pricing, it helped them secure a much longer 12-month contract afterwards.
That's a fantastic outcome, and it directly supports that idea of reshoring, doesn't it? Making local production cost competitive again.
It's a perfect example.
Yeah.
By optimizing the process so drastically, it makes manufacturing that component domestically viable and attractive.
So connecting AML success to the broader picture, what are the typical benefits companies see with this kind of technology? Are there limits? Like, can it fix any old machine?
Okay, good question on the limits. We'll touch on that. But the documented benefits across the board are pretty impressive. First, productivity. We see increases of up to 110% potentially.
Wow.
Yeah, with overall cycle time reductions hitting maybe 53% in some cases. AML got over 20%. Another example, AME saw a 21% cycle time cut. These are big numbers.
Definitely. What about costs?
Cost savings are significant. Typically, users report saving somewhere between, say, $35,000 and $120,000 per machine tool per year.
Per machine.
Per machine per year. Generally, customers see maybe a 15–25% annual cost reduction overall.
Yeah.
And that comes from things like 11% savings just on tooling costs, because you're not breaking tools or wearing them out prematurely.
Makes sense.
Plus, you eliminate all those expensive trial and error runs. Less waste.
And part quality, does that improve too?
Dramatically.
Yeah.
Getting rid of chatter is key here. We see improvements in surface finish up to 40–50%. AMC, that other example, they reported 50% better surface quality, 40% better finish.
So smoother, more accurate parts.
Exactly.
Yeah.
Better dimensional accuracy as well. And related to costs, you get extended tool life because you're preventing the vibrations that cause excessive wear.
And this must be better for sustainability, right? Less waste, less energy.
Hugely important point. Reduced waste is massive. Getting it right the first time means less scrap material, less energy wasted on rework or those prove-out runs.
Right.
It shrinks the environmental footprint.
Right.
And finally, there's even a benefit for proactive maintenance. By running the machine smoothly within its limits, you're putting less stress on it, potentially catching issues before they become big, expensive repairs.
And back to the limits question, does it work on everything?
So the software maximizes the potential of the existing machine tool. It pushes it further than traditional methods could. But, if you have a truly ancient, worn-out machine with fundamental mechanical issues, software can't magically fix that. There's still a physical limit. But for the vast majority of machine tools out there, even older ones if they're mechanically sound, this optimization can unlock significant performance gains without needing to buy brand new, expensive hardware.
Right. Getting more out of what you already have.
Exactly.
So wrapping this up, what's the big takeaway here? What does this deep dive really show us?
I think it shows we're entering a really interesting new phase in manufacturing. These incredibly complex, physics-based problems, things that used to rely entirely on years of human experience and, frankly, a bit of luck, are now being tackled and solved autonomously by software. It's not just making things a bit faster or a bit cheaper.
It's more fundamental.
It is. It's a step change. Production becomes faster, yes, but also significantly cheaper, higher quality, and much more sustainable. It helps tackle those big industry headaches, the skills gap, environmental impact, by using data and smart algorithms.
It's empowering the industry, really.
That's a great way to put it.
So here's a final thought for you, our listener.
This whole discussion, it does raise an important question, doesn't it? If these advanced digital tools, this blend of AI and deep physics understanding, can so radically change a field like precision machining, which seems so traditional, so experience-based. What other industries, maybe ones you know well, could be next? What other fields are maybe sitting on the edge of a similar kind of revolution, where AI and deep expertise come together in unexpected ways? Where else could we see this kind of transformation? What industries do you think are ripe for a deep dive like this one?